Hi, and welcome to Module 5. In this module, we'll examine the nature of light and its relationship to electromagnetic radiation. Stars emit various forms of energy. We term this energy electromagnetic radiation. This section introduces the structure of energy in the universe.
Welcome to our section on the nature of light. The image you see on your screen is a vast star-filled region of our Milky Way galaxy. The glowing colors are emitted from huge regions of gases among the stars known as molecular clouds. The region of space between stars is termed interstellar space.
Light is a form of electromagnetic radiation. Therefore, it is a form of energy. Historically, white light, or sunlight, was considered pure and perfect. The colors in the rainbow, or in a glass prism, were faults due to scattering in the atmosphere or the glass. For an analysis of Newton's discovery, review the Unit 1 lecture notes. In 1666, Isaac Newton discovered that sunlight is actually composed of 7 primary colors: red, orange, yellow, green, blue, indigo, and violet. This is the visible color spectrum of electromagnetic radiation. Newton discovered that the order of colors, from red to violet, do not change order regardless of the orientation of the prism. In 1704, 38 years after he first bored a hole in the window shutter of his bedroom, Newton finally published the results of his monumental work in a book entitled Optics.
Newton's problem of primary colors. If sunlight is not pure and perfect, but is instead made up of 7 colors, none of which are the source of heat from our sun, what are the colors? The best Isaac Newton could say is colors are primary components of sunlight, which was his way of saying he had no idea of the physical nature of this energy. William Herschel proved that heat was invisible energy and primary, but he also had no idea of the physical nature of this energy. It was not until after the discovery of electricity, the electric charge, and the nature of magnetism in the mid-1800s that the actual physical nature of light would emerge over the 19th century.
Today, we say that a beam of white light is separated into its component wavelengths, each of which appears to the eye as a different color by dispersion in a glass prism. White light is a mixture of electromagnetic waves of different frequencies, each of which produces the visual sensation of a particular color. It was Newton who coined the term spectrum for the rainbow of visible light. Color is the ROYGBIV part of the much larger electromagnetic spectrum. Hey, Professor, we should remind everyone what the ROYGB mnemonic thing is all about.
Right, good pickup, Nova. In astronomy, we speak the letters as a memory aid word to help us remember the order of colors in the electromagnetic spectrum. Color is what we call the ROY-G-BIV portion of radiation. And so there you go. You have an easy way to remember the order and the frequency of vibration of this radiation. Just say to yourself, ROY-G-BIV, and you instantly know that the order of spectrum colors are red, orange, yellow, green, blue, indigo, and violet. We will meet several other acronyms in this course that are even more amazing.
The figure above shows the range, or spectrum, of electromagnetic waves. The human eye can detect only light waves, a special form of electromagnetic waves, in a very short frequency band of the EM spectrum. It shows the long-wave radio frequencies to the short-wave UV, X, and gamma frequencies. Again, note that the visible color spectrum occupies just a thin sliver of the entire EM spectrum of radiation. Infrared radiation, or heat, has lower frequencies than those in visible light, and ultraviolet radiation has higher frequencies. Still higher are the frequencies of X-rays and of gamma radiation from atomic nuclei. The bottom image is a visualization of the meaning of wave frequency, the number of cycle vibrations per second. Electromagnetic waves are waves without matter. In 1864, James Clerk Maxwell proposed that an accelerated electric charge generates combined electrical and magnetic disturbances able to travel indefinitely through empty space. These disturbances are called electromagnetic waves. EM waves are nearly impossible to visualize because they represent fluctuations in invisible fields that are themselves difficult to form mental images of. But they do exist. Light, radio waves, UV rays, and X-rays are all forms of electromagnetic waves. Like all waves, EM waves carry energy from one place to another. Thus, Maxwell created a single theory to account for electricity and magnetism that is today the foundation of the entire subject. Before we detail Clerk Maxwell's work on electromagnetic waves, let's step back and watch what Professor Quasar has to show us about magnetism and electricity and some of their relationships.
Welcome to Magnetism and Electricity, Maxwell's work, the connection. First, let's look at magnetism. Two bar magnets here, or two U-shaped magnets. Here you see two straight bar magnets. Here's a compass. What affects a compass? Does electricity affect a compass? No, only a magnetic field given off by iron affects a compass. It has nothing to do with electricity. The magnetic field is also an invisible force field capable of moving objects. Why is this nail moving? The magnet is not touching the nail. It's called the magnetic force. It's an invisible force field. And you can pick stuff up with it. Okay? Magnetism. Magnetism is so strong that if we take two refrigerator magnets of opposite polarity and I ask you to stick them together, you can't do it no matter how strong you are because the magnetic force is stronger than any human being. And the only thing that affects the magnet is, or the compass is a magnet. And then we have our friend electricity. All right? What makes electricity? Yes, a wire and a bulb and a socket, yes, some power plant, okay? But we certainly can't make electricity by that, or I can't put it in my hands. We need some kind of generator, right, in order to produce electricity. Well, in the early 1800s with James Clerk Maxwell, he did some other experiments with magnetism and electricity, and this is one of them. He was very intrigued by this fact that there's a magnetic force that can move things. And he reasoned if a magnetic force can move things, then if I generate an electric field, which this is just an electrical wire with a switch in it, Maxwell figured that he could make an electric field make a magnetic field move. And watch what happens to the compass needle. It's moving, but nothing is touching it. I'm merely passing electricity through a switch, right, making the magnet spin. This shows a relationship between electricity and magnetism. So what's that all about? Well, I have a demonstration that a colleague of mine and I built many years ago, okay, which shows Maxwell's understanding of electricity and magnetism, which is today the basis of our entire modern world. So what you see before you is some bar magnets that are, or some U-shaped magnets that are stood up on end, and I have a bar magnet going down the center of it with a crank handle. All right? This is not a joke. There's no wires. It's not connected to anything. And notice that I have a light bulb, a regular light bulb that we just saw lit, connected to a socket that connects to nothing but the magnets. Now watch this. As I make the magnetic field move through the magnetic field, it produces an electric current. Here I'm creating electricity from magnetism. And not only that, the electricity that is being generated is technically an electromagnetic wave, okay, of vibrating electric and magnetic charges that is glowing at 550 nanometer. And if I just pull this one tiny wire, copper wire, what flows down the copper wire to make electricity? Electrons, that's right. Okay? And without it connected, I can spin all day, I get nothing. Okay? I connect it to the end, I spin. Okay? This shows that the magnetic field is producing a flow of electrons that move down the wire and create electricity. The electricity then generates an electromagnetic wave vibration of about 550 nanometers, and we get what's called electromagnetic induction. So what, Professor Geiger or whatever you are? So what? You get this, a motor, the full reason of the 21st century. Notice, iron, copper, this makes a motor, this makes it spin, this makes our modern world. Electromagnetic induction, James Clerk Maxwell. Y'all have iPhones, phones, and pads and things. You ever notice that big heavy thing on the end of the wire there? Well, if you cut one open, you'll discover that it's a big piece of iron surrounded with hundreds of pieces of copper coil. Electromagnetic induction. Maxwell's understanding that magnetism generates electricity and electricity generates magnetism, and from that we can make circuits that then make motors, which is our whole 21st century world. Thank you very much.
Maxwell deduced that EM waves exist and travel at the speed of light, and that light itself was an electromagnetic wave. The wavelengths of electromagnetic radiation are so small they are measured in a special SI unit called the nanometer. 1 nanometer is equal to 10 to the negative 9 meters, or 1/1,000,000th of a meter. The wavelengths of visible light are radiated in the range from 700 nanometers, red, to 400 nanometers, violet. Since light waves are actually oscillations of linked electric and magnetic fields, they naturally have the properties of all electromagnetic waves. The following are important quantities for all EM waves. Wavelength is the distance between two consecutive waves and is represented by the Greek letter lambda. Frequency, the number of waves sent out each second, is represented by the letter F. Velocity, the speed with which the waves travel, is represented by the letter V. This yields us the following equation. Wavelength is equal to velocity divided by frequency. The velocity of all electromagnetic radiation in the universe is constant. And what is that constant, class? That's right, Einstein's constant c. So c is the speed of light. Or more technically speaking, c is the speed of all electromagnetic radiation through space. UV radiation, infrared radiation, radio waves, microwaves, X-rays, etc. all travel at the same speed. In the early 20th century, the quantum theory of light was developed. Light is radiated in the form of tiny packets called photons. The quantum theory of light was proposed by Max Planck and Albert Einstein to account for the behavior of radiation at the atomic level. Photons in vacuum travel at 186,000 miles per second, which is the speed of light. Each photon has associated with it a particular amount of energy. For example, in blue light, the photons have more energy than in red light. In X-rays, the photons have more energy than in blue light, etc.
In this module, we learned about the nature of light, electromagnetic waves, wavelength, frequency, velocity, the quantum theory,